Hi, I'm Jessica, and I'm going to be talking about teaching data-oriented design. In particular, I'll be talking about teaching it in this particular video as an elective. I've actually taught it in a couple of classes. One course I taught it in was an intro course for transfers, and I'll talk about that in another video. This particular video is going to be about teaching it as an advanced elective in a co-listed class with master students and undergraduate students. And the big thing to note about this is I've only taught this course once before. And so there are some things that I'd like to change about it, and I'll talk about that as well. First of all, let me start with some of the good student outcomes I saw from the class that made me very happy that I taught it as a class. The big thing for me was that students thought more about the structure of their code in general at the end of the course. And several of the senior students got jobs at really good game companies like Epic Games and Sony San Mateo. The students also tended to profile their code when trying different things, and they tended to use the profiling to be able to ask questions about, well, why is this better, or why is this not as good? And they used the profiling in order to help solve their problems, which they did not tend to do when they came into the class. So that was a win for me. They also considered data-oriented design for solo projects. Even when they weren't using the full paradigm, they used some concepts from it, which was good. There were some interesting and problematic outcomes as well, things that kind of surprised me. The big thing that surprised me was that students tended to link the concept of data-oriented design with optimization. And so there was at some point in the class when everything I talked about, it was like, oh, this is optimization. And even when it was not, so I'm going to really have to work hard in the future to make sure that they can understand the difference between good engineering and optimization, because they're two different things, and the students really got those concepts confused in that class. Also, when students exited the course, and I did see a lot of the students after they left the course, especially when they were master students and they went on to do their capstone project, they decided not to use data-oriented design in a lot of cases because they were the only student in their group that knew data-oriented design. And so it was kind of, nobody but me knows this, therefore I have to do things the way they want to do things. Whether it's the better way or not, I have to do it this way. And so I think in the next class, I'm going to talk a little bit about, how we can try to overcome some of those issues. Because of course you don't want to be the person in your group that's telling everybody else what to do, but you also don't want to just completely give up and say, I don't care how it runs, because that's not good either. So I'm going to have to work on that. Also, sometimes the students consider data-oriented design to be experimental because Unity Dots itself is still being developed and it's still on preview. And so students were like, oh, this is a new thing, it's still experimental, and that I actually needed to talk more about how some of the Unity projects are actually have been commercialized, especially on mobile platforms, and that it is not experimental for some people. There are specific skills that our students have coming into the course. They have knowledge of both C++ and C# when they come in, so therefore I can use examples from both languages, which is convenient. They also are used to object-oriented design. They commonly believe that it must be the paradigm that they use because it's the only paradigm that they really know at that point, and they've seen it in most of their classes. And so I have to convince them that they should consider something else. They have had some basic threading. They normally forget it. They normally don't use it throughout their career at our university. They have not usually profiled their code. And this is really during week 1 in my class. They are going to profile code, and they are going to continue to profile it throughout the entire semester. This is a basic outline of the course. Of course, we have to introduce people to, well, what is data-oriented design, and how do you profile your code if you don't know how to profile it? Because you're going to be doing this a lot. I also give a review of things like version control and things like that, since we use that throughout the course as well. And then I start talking some about hardware concepts and lower level programming languages, and how the hardware influences those. Then I go into some data-oriented concepts, data structures. You notice in the course it kind of starts out low level and then it gets higher and higher and higher level. That's sort of the structure of the class. And of course, the most important thing is week 1. What in the heck is data-oriented design? And for me, there's a whole bunch of things that you consider in the paradigm, but the most important 2 things that I think are just things that I need to really push at students the most. The biggest one is that it really involves a holistic view of software development, and that takes everything from the hardware up to the compiler up to the executable into account when you're making software. And I think that's important because in most fields you look at, that actually is how they consider things. They consider, the breadth of everything that's involved in the construction process. And in software, we commonly say, oh no, that hardware thing, we don't have to worry about it because it's fast. Therefore, just kind of ignore that thing. And that's actually really common in software for some reason. And I actually think that data-oriented design is kind of cool because it considers the hardware as being important too. And that's part of why it works better, is that if you consider things that actually work well in the hardware, it's going to be better. Go figure. And of course, the other very important thing about data-oriented design is that it views all software from the concept that it is input, transformed, and then output, and that is all a computer does. And so everything you do when you write software is about inputting data, transforming it, or outputting it. And so it breaks it down into a very simple way of thinking about it, which is interesting because students have never thought of things this way. They commonly don't even know what the data in their programs is. And so we have to do some things to get them to think about that. A couple of notes: code tends to be shorter using data-oriented design, and it tends to run faster. Profiling code is a core part of testing it. And also, I use some other slides in order to help convince them that object-oriented design and data-oriented design are 2 very different things, and that the data-oriented design works better in general than just this sort of object-oriented design they've been doing. And I've got a link up there to a GitHub that actually has a set of slides. He actually uses the version control in GitHub to go through several versions of his code, and you can look at each one and see how it gets better as he changes things in it, and it's just kind of nice to watch. And it's a really big difference in terms of performance at the end. So it's a very good example. The second week, I actually start talking about some simple hardware. The Atari hardware, it was really a simple piece of hardware. I talk about the assembly language because for our particular program, since we're not a CS program, the students actually don't get an assembly level course. And so in order to understand this whole input, transform, output paradigm, it helps to see the assembly language. And the Atari assembly fits on a page. It's simple. They also see their first hardware diagrams. The one for the Atari is actually a really simple hardware diagram. And the other thing is that if you look at the opcodes, They can actually be cycle counted. So you can look at different ways of writing programs, and you can see that they have different cycle counts. So they have a different performance cost depending on how you write things. So if you do loops, it's more expensive than if you just copy things several times in terms of the cycles. And so they can actually start to reason about, well, if I do this, it might be a bit more expensive than if I do this other thing. And it also helps to motivate why hardware designs changed and things like branch prediction became a very important part of hardware. Here are some great resources. I'll have the slides available so that people can actually go and look at them if they're interested in doing this. So I spent 2 weeks on more modern hardware concepts. Again, we look at several diagrams. We look at how hardware has changed. The biggest change, of course, that has the most impact, that we spend the most time on, is cache. In fact, if you don't have room for anything else in a course, cache is the most important thing to talk about it because it's going to have the most direct impact in terms of performance. But in this particular course over those 2 weeks, we talk about other concepts such as pipelining and superscalar and branch prediction, and then we talk about how things became multi-core, and then we go back to cache, because cache is always the most important. In fact, this is one of my most favorite pictures of an AMD Opteron chip, and it shows very clearly that cache is over 50% of the chip, so it must be important, right? After talking about the hardware, this is when my students started to believe that everything I talked about had to do with optimization. Every single thing, even when it didn't. And so this is where I'll have to do better next time, because apparently anything related or considering the hardware is optimization, even when it's not. So this is, where I could do better and talk about optimization versus good engineering. And here are some of the things that the students thought was optimization that I call good engineering. And that's things like taking invariants out of loops so that you don't keep resetting variables over and over again in a loop, and don't keep redoing calculations, which commonly they're redoing calculations over and over again in a loop when they don't need to. And you don't recreate and destroy things on a frame-by-frame basis, which is another thing that you commonly students do over and over again. Access arrays in terms of memory order and don't skip around. So for C++, this means go across by the row, because that's memory order, and don't go down the columns. And so if you've got a couple of different ways, like in an image, of accessing each element of the byte array, then you should make sure to do it in memory order, because then the cache works well with you. And if you're going to write multiple conditionals, do it with the most frequent case first. I did not believe how often I saw that students consistently will start with the extreme cases first, the exceptions, and then they'll get down to the most common case, the last one. And that's the backwards way of doing it. And so the other thing, of course, design software for the common case, which tends to be many of something as opposed to one of something. They're very used in object-oriented design to design one and only one. And then when they have to scale it to many, it gets messed up. So do it the other way around. Design it for many, and then if you've got a single case, then it's a special case. So another couple of weeks, memory allocation and allocators. I don't go really deep into pool and stack allocators. They don't write them themselves or do anything like that. This is just, a basic introduction to some of these concepts. I actually go over data-driven design because students don't necessarily know what the data in their programs is. And for games especially, if you're doing data-driven design, you can say, well, what was in that level that you loaded into your game? What were those, what was that content? What were those audio sounds? And then all of a sudden they're like, oh, that's data. And it kind of helps them to think about things in terms of data. And then they can slowly begin to think in terms of things, data they actually create within the game, which has to do with the game logic. We talk about structures of arrays, which is more often used in data-oriented design, and arrays of structures, more often used in object-oriented design. The entity component system design pattern, which for students makes it really, really easy to think, oh, the components are my data, the system are my transformations. And that's very helpful in terms of thinking about how to put things in a data-oriented construct. We talk about batch processing, when batches of things are the common case as opposed to single cases. And I actually spent a couple of weeks on data structures. Some of it is review, and to say, well, we have some data structures that have very good locality for cache reasons, and we should use those. And of course, I also talk about, things like linked list, which are very bad for locality in general for most cases, unless you have very large data. And then, I talk about things like spatial hashing. An example is in the Boids demo from Unity. And the importance of custom data structures, because I've talked to a lot of industry people that say they see a lot of students come out that are afraid to write their own data structures because they've been told the STL is the end all and they should never do anything else. And that is not the case. There are lots of custom data structures out there. If you have a problem that one of those data structures doesn't exactly fit, you write your own custom thing. You solve the problem, and the data structure helps you solve the problem. It's not just algorithms. And so I talk about one particular data structure like that, which was written by Matthew Bentley. It is called the colony data structure. I've got a link to it there. Again, slides available at the end. And he uses his data structure for large arrays of unordered objects that need to change a lot, but things like where they're located need to remain consistent so that they can still be accessed, even when things exit and enter. Here's what I wish I would have talked about during weeks 9 and 10. In reality, I talked about PS4 console development in terms of multi-platform development, which was too big of a topic. It was way, way obnoxiously larger than it should have been. And I will not be doing that again. So I'd rather do SIMD and talk about things like useful math and physics and CPU SIMD as opposed to GPU compute and how to do those different things for a couple of weeks. Basic introduction. And then the rest of the time, I talk about the Unity data-oriented tech stack because it's actually a really good example of data-oriented design and an entity component system. The way they deal with archetypes is quite nice. And before I start this though, I usually have to review threads because they usually don't remember them very well. So that's an important thing to know about. Then the Hello Cubes example, which the picture is up on the slide, they have several different examples which show different ways of using the Unity's job system. And they're very good. They help explain the basics. There are a lot of sample programs that you can port from object-oriented design to data-oriented design that are also very nice. So their job system is a great way. So once all of the students learn what the data is and how to break things up in terms of data, they can start doing more data parallelization, which job systems are great with that. And so this is actually helpful because Unity has a job system built in, and that's my favorite part of the Unity dots. Here are some resources that I use in terms of teaching dots currently. Okay, other course information. So generally speaking, the overall course, I have 2 exams during the semester, and then several projects and homework assignments that are graded. There's a final project that is suggested by the students, which is either tends to be a Unity project that is one of their sample object-oriented projects ported to a data-oriented project, or it's a current game project, current game engine that they want to make more data-oriented. I allow them to do either one of those things because they're highly motivated when they get to choose their own project. Future work, I actually don't think this is the best way to teach data-oriented design. I actually wish it was sooner in our curriculum, but changing the core curriculum is a really, really difficult task. And there are lots of people involved in it, and it's really difficult. If it was pervasive in the curriculum, this would be a much different course. Sometimes when students take downstream electives, this course can impact them. I know that I taught a game AI elective where one of the students in it had taken my data-oriented design course, and he was writing a Blackboard system that he took the Blackboard out of because it wasn't really necessary because he had 2 agents and an arbiter and they could just talk to each other. However, it wasn't a Blackboard at that point. And I was lucky in that I had taught both courses, so I knew exactly what he had done, and I talked with him about it. But if it doesn't have a Blackboard, it's not a Blackboard system anymore. So it's one of those things, you gotta watch some of the things the students do because they're like, this code is not necessary, and then they kind of chuck it. So that's some of my future work. And with that, I believe my talk is at an end. So thank you very much for listening. And if you want, you can contact me. My email address is right there.